Sometimes science feels like straight up magic. And today, we're diving into something that is just that, peeking into the atmospheres of planets that are light years away from us. We're talking about reading the air on worlds we can never actually visit to figure out what they're made of, what their weather is like. It's an absolutely incredible feat. So let's get into how it's even possible. So let's just start with this puzzle right here. Think about it. How on earth do you take the temperature of a planet that's trillions of miles away? A world so distant its light has been traveling for centuries just to reach our telescopes. It's a staggering challenge, but believe it or not, it gets even harder. Because here's the real kicker. That tiny little planet is practically hugging its star. Trying to see the faint light from its atmosphere? It's like trying to spot a tiny firefly buzzing next to a colossal stadium searchlight from a few towns over. The star's light is just so overwhelmingly bright, it completely drowns the planet out. So how do we get around that? Okay, to really get a handle on this, you gotta understand the scale we're dealing with. We've found thousands of exoplanets out there. It's amazing. But for almost all of them, they're just dots on a chart. Knowing a planet exists is one thing. Knowing what its sky actually looks like, that's a whole other level of difficulty. See, the problem is this. The light from the star is a deafening roar. And the light that is actually bounced off of or passed through the planet's atmosphere, well, that's the faintest whisper you can possibly imagine. For decades, that whisper was just completely lost in the noise. But then, scientists came up with a truly brilliant solution. So how did they crack this impossible problem? Well, here's the clever part. Instead of trying to block out the starlight, which is almost impossible, they figured out a way to use it. They developed a technique that could actually listen for that planetary whisper and pick it out from the star's roar with incredible precision. And that secret weapon is called high-resolution spectroscopy, or HRS for short. The easiest way to think about it is like this. You know how a prism splits white light into a rainbow? Well, HRS does the exact same thing, but on a mind-bogglingly detailed scale. It creates a rainbow with millions of different shades. And hidden inside that super detailed rainbow, every single atom and molecule leaves behind a unique barcode, a chemical fingerprint. So here's how it all goes down. First, our telescopes grab all the light from that distant star system, the roar and the whisper all mixed together. Then, this HRS technique splits that light into its incredibly detailed spectrum. And finally, and this is the real genius of it, some very clever processing allows astronomers to basically subtract the star's light, leaving behind only those faint, unique fingerprints from the planet's atmosphere. It's an amazing way to read alien air from so far away. All right, so we've got this amazing tool. What have we actually found with it? Well, this is where things get really, really cool. The source for this explainer, the Annual Review of Astronomy and Astrophysics, points to some groundbreaking discoveries that are totally changing how we see these other worlds. First up, we've learned that the absolute hottest planets, these things called ultra-hot Jupiters, have atmospheres that are so scorched they basically look like the outer layers of a star, just full of vaporized metals. But what's also wild is that many of the other gas giants we've looked at seem surprisingly familiar, with chemical makeups that look a lot like our own sun. And then there's this really weird pattern they found. The hotter gas giants almost always have what's called an atmospheric inversion. That means their upper atmosphere is actually hotter than the layers down below, the total opposite of what happens here on Earth. The cooler gas giants don't have this. This clear split tells us there's some kind of fundamental switch in the physics of an atmosphere that flips at a certain temperature. Okay, this next one sounds like it's straight out of a sci-fi movie. Scientists have found planets that are literally evaporating. They're so close to their stars that their atmospheres are being blasted off into space, and this HRS technique can actually see the enormous, comet-like tails of helium gas they leave trailing behind them for millions of miles. It's like we're watching planetary evolution happen in real time. And finally, this is just so cool. The technique is so sensitive that it's like we're running a planetary DNA test. We can now spot different versions of elements, called isotopes, ones that are just a tiny bit heavier or lighter. The exact ratio of these isotopes is like a fossil record, giving us powerful clues about where in its solar system a planet originally formed billions of years ago. As incredible as all this is, believe it or not, this is just the opening act. The technology behind all these discoveries is about to take a massive leap forward, and it's going to open up a whole new universe of possibilities. So what's this giant number all about? Well, get ready for this. A new generation of extremely large telescopes is about to come online. According to the research, these new observatories are going to boost the speed of this HRS detection method by up to 3 orders of magnitude. In other words, we're about to be able to analyze these faint alien atmospheres 1,000 times faster than we can right now. And that massive leap in speed, it brings us right to the edge of the ultimate prize. As the research paper puts it, this new power promises to bring temperate rocky exoplanets into view. We're talking about finally moving beyond just the giant hot planets and being able to aim this incredible tool at smaller, cooler, potentially Earth-like worlds. And that, of course, leaves us with the biggest question of all. Once we can finally read the chemical barcodes in the skies of these rocky worlds, what are we going to find? Will we see the fingerprints of water, of oxygen, maybe even methane? What stories will the air of a second Earth have to tell us?